Let's study 10th standard ICSE Physics Chapter 8, Section B and C. That is EMF, voltage, combination of resistors and electrical power. Imagine that in a circuit, we are using a cell of 6 volt. So you purchase a cell or a battery of 6 volts which supplies current in the circuit. There is a load here with a resistance, a device which works on this electricity. Now, if we measure the potential difference across the 2 points here, if I use a voltmeter to measure the potential difference, we will notice that it is not 6 volt. It is a little less than that. Let's say 5.8 volt. But the cell was of 6 volt. No, don't go and return the cell, because this would be the case with any cell. Even if you use a cell which lasts long, very long, but still there is a potential difference drop called a voltage drop. You see, the potential difference is defined as the work done to carry a unit positive charge from one point to another point. That is from the positive terminal of the cell across the entire circuit to the negative terminal of the cell. But the truth is that the charge has to travel back to the positive terminal too. That means there is movement of charges inside the cell as well, which makes sense because we know that it is the chemical reactions inside the cell in the electrolyte which produces this electrical energy. So the charge has to overcome the external resistance, of course, but the charge has to overcome the internal resistance as well. That's right, every cell has some internal resistance too, which is shown here outside. So consider this as the entire cell, which we represent in a circuit with 2 lines, and this is how we show small r, which is called internal resistance, due to which you can think that some of the work done is being used up in overcoming this internal resistance. So the work we get outside is a little less, or you can say that we won't get the entire 6 volt, we will get say 5.8 volt in the entire circuit, which is still fine because 0.2 volt is not a huge drop thanks to the small internal resistance in the electrolyte. So that means that the voltage drop due to the small r was how much? 0.2 volt. That's right, that's called the voltage drop. And 5.8 volt, that's called the potential difference in the circuit. If you add them, you get 6 volt. What's that? That is EMF, electromotive force. So it is defined as the amount of work done in carrying a unit charge from one point, say the positive terminal, then through the entire circuit, and then even across the cell back to the original point, that is back to the positive point. So that totally is called EMF. So EMF is equal to potential difference plus voltage drop. So obviously EMF's unit is the same, volt. It's called electromotive force, but actually it's not a force. It's similar to potential difference. In fact, if you switch off the key, if there is no current flowing, then there will be no voltage drop. And in that case, we can say that the EMF is equal to the potential difference, which is 6 volt. There will be no drop in potential difference in that case. Of course, if the circuit is off, no device will work. So if you want the device to work, you have to accept the fact that there will be a slight drop in the voltage. You won't get the entire EMF being put to work because there is no such cell with no internal resistance. It's like you refill your mobile phone with 50 rupees recharge, but the talk time you get is not entirely 50 rupees. You have to pay some taxes perhaps. So the talk time you get is just, let's say, 45 rupees. So the electric cell, which is somewhat like this, it has an electrolyte. Of course, the cells we use don't have a liquid electrolyte. It's a semi-solid paste inside. It has electrodes, one which acts like a positive terminal and the other as a negative terminal, which simply means higher potential and lower potential actually. And current is assumed to be flowing from higher potential to lower potential in the circuit. But inside the electrolyte, we imagine it moving from the lower terminal to the higher terminal, higher potential that is. Actually, the ions, the cations and the anions move towards the respective electrodes in the electrolyte, and in the circuit, electrons flow through the metallic wire. But it is because of the chemical reactions in the electrolyte, it is because of the potential difference that there is a push on the electrons to move in the circuit. If these chemical reactions won't happen, there will be no push for the electrons to move in the circuit, and there will be no current flowing. So the EMF is defined keeping this energy being spent in mind. So one way to calculate EMF is the total work done upon per unit charge. That is exactly how we had calculated or found the formula of potential difference as well, but the difference is that here the work done is from the positive terminal to the negative terminal, that is only across the circuit. But here it is around the complete circuit, that is the circuit outside the cell as well as inside the cell, the electrolyte inside the cell, both combined. And the difference between the two is called the voltage drop. So you can say voltage drop is the amount of work done in carrying a unit charge, a unit positive charge, through the electrolyte inside the cell. So the total EMF is potential difference plus voltage drop. Now this is the difference between EMF and terminal voltage. First is the definition. Secondly, this does not depend on the amount of current being drawn from the cell, because if you buy a cell of 6 volt, then the EMF will always be 6 volt for the life of the cell, assuming that the conditions are normal, that is the temperature of the environment, etc. The terminal voltage of the cell, however, depends on the amount of current being drawn. If you use an appliance which is using a lot of current, then there will be a lot of voltage drop as well. So the terminal voltage will become less. So if this device was using a lot of current, then perhaps the voltage drop won't be just 0.2 volt, it would be 0.5 volt. So now the potential difference across its ends is 5.5 volt, not 5.8. So the voltage drop depends upon the amount of current being withdrawn, and so does the potential difference. Whereas EMF doesn't depend on that. The third point is that EMF can be equal to or more than terminal voltage, and the terminal voltage can be equal to or less than, but never more than EMF. There is one case in which the terminal voltage can be more than the EMF. That is when you are charging a cell. So if you remove the cell from the circuit and you put it for charging, let's say it's a rechargeable battery, and if you put it for charging, so when you charge it at your home plug point in the socket, what is the potential difference there? Well, it's 220 volt. So the potential difference is 220 volt, even though the EMF is just 6 volt. So in that case, terminal voltage is greater than EMF. But that's just an exceptional case here. Next, let's talk about internal resistance of a cell. We know what is a resistance in a conductor. We had studied in 9th standard that while electrons are drifting in a copper wire, they crash. No, I didn't mean crash landing on you. It means the electrons just bump into each other and the ions present, and that is the cause of resistance of the wire and also resistance of any appliance. But internal resistance is due to the electrolyte inside the cell. That is the reason why there is a drop in the voltage. So even that is measured in ohm. So when you want to measure the total resistance of a circuit, actually you have to consider this internal resistance also, whose formula is V is equal to IR. V is the voltage drop, I is the current, which is the same externally and internally, same current, and R is the small r is the internal resistance. And that's how you represent the internal resistance. Learn this diagram, practice it, because this can be asked in exam. Next, what are the factors affecting internal resistance of a cell? There are 4 factors. First of all, surface area of the electrodes. Larger the surface area, less is the internal resistance. Distance, well, more the distance, more is the resistance, makes sense. Nature and concentration of electrolyte. Less ionic the electrolyte, or higher the concentration of electrolyte, greater is the internal resistance. So more concentration means more resistance, or less ionic, which means it is not able to form the cations and anions freely, easily, then the resistance will be greater in the electrolyte. And finally, the temperature. Well, surprisingly, higher the temperature, less is the internal resistance. If you remember a normal conductor like a metal, there, more the temperature, more was the resistance. But then we studied for a semiconductor like silicon, germanium, more the temperature, less was the resistance. And even electrolyte is exceptional, because even here, more the temperature, less the internal resistance. Next, let's talk about combination of resistors. Now, in the reduced syllabus, all these derivations are all cancelled. We just have to learn one formula. If the resistances are in series, that is connected one after the other, then the total current flowing through them is always the same. And the resistance, total resistance, will be calculated by just adding them. Say 2 ohms, 3 ohms and 2 ohms. So the total resistance is 2 plus 3 plus 2, that is 7 ohms. By the way, there will be some internal resistance small r also, let's say 0.2 ohm. So we might have to calculate that as well. So it will become 7.2 ohm, the total resistance. Even this is in series with the rest of them. So in a numerical, which we'll do next week, if there is a mention about a potential voltage drop or internal resistance, then keep that in mind. But in any numerical, there is no mention of it, then we can just ignore the internal resistance. Also remember, in series, the potential difference across each resistor, that is between AB or between BC or between CD, if you measure with a voltmeter, you will realize that the potential difference may be different. So if this is 2 volt and this is 3 volt and this is again 2 volt, so the total potential difference was 7 volt. So you can add the potential differences here. Although the current flowing through them will be same. If you use an ammeter here, you will see the same 1.5 ampere flowing through each of them and through the entire current. So keep that in mind. So resistors in series are used when you want to increase the overall resistance, or you want the same current to be flowing through them. But keep in mind, if you use them in series, if one of them gets fused or stops working, or you switch it off, that breaks the entire circuit and all the devices will stop working. So that's a disadvantage of series combination. So the total resistance formula is R is equal to R1 plus R2 plus blah blah blah. Next, combination of resistors in parallel. So a differentiate for 3 points you need to remember between series and parallel. So in parallel, you can see they don't have to be mathematically parallel to each other. No, they can be non-parallel as well. It's just that there should be different paths for the current. This current, let's say 5 ampere, was flowing through the circuit. After reaching here, it had 3 paths. So which path would it like to take? It would like to take the road not taken. But actually it would split up into 3 parts: I1, I2 and I3. And of course all of them will join back. That is very important. They have to split and they have to join back. And again, those, did I say 5 ampere? 5 ampere will come back here, completing the entire circuit. But how will they be divided? Well, that totally depends on the resistance. It depends on the ratio of resistance. In fact, current is inversely proportional to resistance out here. So whichever has the highest resistance, let's say 2 ohm, 3 ohm and 5 ohm, whichever has the highest resistance will have the least current flowing through it, which makes sense if you have many cars moving on a highway and there are 3 roads and they want to get to the same destination. So if they realize that this particular path has the highest resistance, then the least number of cars will enter this road, and the one which has the least resistance will have maximum current flowing through it. So when we'll do numericals, we'll have to keep this in mind while calculating I1, I2 and I3. Note that since these 3 resistors are between the same 2 points AB, if I connect a voltmeter in parallel, yes, voltmeter is always connected in parallel, I will notice that the potential difference across each of these is exactly same. So in series, the potential difference need not be same across each resistor, but the current flowing is same. Whereas in resistors in parallel, the potential difference across each of the resistors is the same, but the current flowing may be different. So that's the difference between series and parallel. And here, if one of the resistors fuses, it stops working, still the current will continue flowing because there are other paths for the circuit to be completed. But how do we calculate the total resistance of this combination? Well, we know that I1 plus I2 plus I3 is I. So using that, we can actually derive the formula, although you don't have derivation this year, it's reduced syllabus. But the formula is the reciprocal of the resistance in parallel is equal to the sum of the reciprocals of the individual resistances. So we'll be doing a lot of numericals based on this formula. One very interesting fact about this is that if we have three resistances, let's say 1 ohm, 10 ohm and 100 ohm, okay, and if we connect it in series, then the total resistance is 111 ohm. That is more than the individual resistances. But if we connect it in parallel, let's calculate what will be the total resistance here. So I got 1 upon 1, 1 upon 10 and 1 upon 100. Remove LCM, add the numerators, 1 upon 100, which is the answer of 1 upon RP. This is a silly mistake which many students do. Please remember, in the end you have to reciprocate it. So 1 upon RP is this. So RP, that is resistance in parallel, is 100 upon 111, which is 0.9 ohm. That's it. That is less than all of these resistances individually. So unlike in series, in parallel, the total resistance is less than the each individual resistance. So that's another point of difference and a huge benefit for resistance in parallel. Apart from the fact that the circuit is not broken easily, the other advantage is that it reduces the overall resistance. And you know that less the resistance, more current can flow through the circuit. So that's why all connections in our households are always connected in parallel, so that each has a independent circuit and also the total resistance decreases. Note that I have not talked about the internal resistance here, but if there was an internal resistance, let's say 0.2 ohm, then the overall resistance will be this, which is 0.9 ohm, which I just calculated, plus 0.2 because it is in series with this combination. So the final answer would have been 1.1 ohm. But what if you are given an example in which you've got two of them in parallel and then one of them in series? We'll be doing many numericals of this type, which is quite fun and very important from exam point of view. So first we'll calculate this. 1 upon 1 plus 1 upon 1 is 1 plus 1, that's 2. So this total is 2 ohms. Even after reciprocating it, no, so that's a big mistake. So 1 upon 1 plus 1 upon 1 is 2, but that is the answer of 1 upon RP. So if you reciprocate it, the resistance in parallel is half. Actually, the resistance of this combination is just half ohm. And this should be very obvious to you. How can the combination of a parallel resistance be more than the individual resistances? It has to be less than that. So it's half a ohm. And this half ohm is in series with 1. So now what is the total resistance? 1.5 ohm. That's right. Now, if you're given a graph, it's an IV graph, by the way, not a VI graph. In an IV graph, the slope of a graph gives you the conductance. That means steeper the slope, more is its conductance, and less is the resistance. If it was a VI graph, then the slope would directly give you the resistance, but it's an IV graph. So this one has a less resistance and this less steep graph has more resistance. So clearly this has to be for a series combination and this has to be a parallel combination if that's the choice we are given. Now let's talk about electrical energy. Electrical energy can be converted into various forms of energy using equipments. Heat energy, well, using a heating element, electric heater, oven, geyser, etc. Light energy, well, in electric lamps. Kinetic energy, in electric motors used in fans, mixers, etc. It can be converted into chemical energy, especially when you are charging a battery, like a lead acid accumulator, car battery. It can be converted into sound energy using loudspeaker, and it can be converted into magnetic energy using an electromagnet. That is a coil wound around a soft iron bar and current flowing through the coil. Now, measurement of electrical energy. SI unit of any energy form is always Joule. Even electrical energy is measured in Joule. The formula of the energy or the work done is charge into potential difference. We know that the definition of potential difference was the amount of work done per unit charge. So if you cross multiply, the work done, electrical work, or also called electrical energy, because work and energy are two sides of the same coin, is equal to charge into potential difference. But charge is nothing but current into time, so we get the formula VIT for the work or electrical energy. VIT. This is useful for numericals. We can further derive various other formulae if we just substitute the V as IR, or we substitute the I as V upon R, and so on. So these are basically the different forms of the same equation. So VIT, I square RT, V square T upon R. You can use any formula in the numericals based on the data given. I personally like these two formulae, VIT and I square RT. This helps us to solve most of the sums. The SI unit is, of course, the Joule. What about power? Well, power is work upon time. So electrical power is defined as the rate at which electrical energy is supplied by the source. So its unit is also watt. That's the SI unit, even for electrical energy. What about the formula? Well, if this is the formula for work, then just do upon time. So if I do upon time, TT cancel, what is the answer of power? V into I. Or you can do, cut TT here and I square R. So these formulae are mentioned here. They are similar to these formulae, just we have divided it by T. So these are the formulae for electrical power. This is an amazing formula for numericals. So power of 1 watt is equal to 1 volt into 1 ampere. That's a new unit for electrical power. A watt can also be called volt into ampere. So 1 watt is the electrical power consumed when a current of 1 ampere flows through the circuit of potential difference 1 volt. So if you know the formula, you can remember the definitions easily. There are some bigger units as well. The commercial unit of electrical energy. Now, when you get the electric bill, go and have a look at it, BEST bill or your Tata bill, you will notice that the electrical energy consumed by your household is not measured in joule. In fact, it is measured in kilowatt hour. So what is that? Let's understand this, although we have done this in a previous chapter too. Now we know that work is equal to power into time. So if I say watt into second, that is nothing but joule. Joule is equal to watt into second. That's the SI unit. But this is very smaller unit. It's very inconvenient to use this for our commercial purposes. So let's go for a higher unit. Instead of second, what if I take hours? That's good. So we get watt hour. So that is also a unit of energy, watt hour. It is equal to 3600 joule. This is for electrical energy. But even this is too small for our commercial purposes. So let's make it bigger. Instead of watt, let's use kilowatt. That is 1000 watt. So now we get the unit called kilowatt hour. Notice K is small, W capital, H is small, and that is equal to 3.6 million joule, 1 kilowatt hour. And that is called one commercial unit. If you check your bill, you may have used 500 units or 1000 units and so on. And the bill is the number of units multiplied by the rate, which is 5 rupees or 10 rupees per unit. So what is that 1 unit of electrical energy? Well, that's 1 kilowatt hour or 3.6 million joule. So now you know why we don't measure in your bill the electrical energy in joule, because then we'll have to deal with millions of joule mentioned in the bill, which might be a little strange and confusing for many people, and people might just start blaming you for consuming millions of joule of electrical energy by surfing the internet whole day. So that's why we use kilowatt hour. So it's defined as the electrical energy consumed by an electrical appliance of power 1 kilowatt for 1 hour. Next, let's talk about power rating of common electrical appliances. When you go to buy a bulb, you often say, give me a 100 watt bulb or a 10 watt bulb. What is the meaning of that? Well, it simply means that if it's rated as 100 watt, it will use 100 joule of electrical energy per second. That's all it means. And of course, it will be 220 volt because that is a standard potential difference in India across all the plug points. What this means is that this measurement is true only at this potential difference. If you use this appliance, same appliance somewhere else, say in the USA, there perhaps plug points are not at 220 volt. Maybe it's at 250 volt or something else. Then the power rating will be a little different. That is why devices, you have to be careful about using devices of one country in another and check if the power rating is compatible. So this power rating is telling us two things. It is telling us the resistance of the filament or the element in use, and also the safe limit of current. that is R and I. But this is power and this is volt. I don't see any R or I here. Well, we can derive it using these values. So the resistance of the element or the filament in the appliance is V square upon P. That's a formula which we had studied earlier. P is equal to V square upon R. Here we go. P is equal to V square upon R. Cross multiply it. That's how we get this value. What about the safe current? The maximum current which can conveniently flow through it without any problem. That is called the safe current. Well, formula is P upon V. Again, we can derive this. P was V into I. So cross multiply I is equal to P upon V. So how is this information useful? Well, for a bulb which has 100 watt and 220 volt, let's calculate. The resistance will be 484 ohm. That's quite a lot, and that's why we use a tungsten here, because it has a high resistance and so it can convert a lot of electrical energy into light. Notice that this resistance is high because the bulb is glowing and its temperature is quite high. If you switch off the bulb, the resistance is not so much, it's less, because it is not hot when it is switched off. Yeah, even when current is not flowing, it has resistance. Even if you don't take your car out on the road still has traffic, right? What about the safe current? Well, in this case, the safe current turns out to be 0.45 ampere, which is approximately 0.5 ampere, which means that if current more than 0.5 ampere starts flowing through the bulb, it might just fuse, it might just blow off. So we need to restrict the amount of current flowing through it with 0.5 ampere only. But how do we do that? Well, we use fuses. A fuse is a device which prevents excess current from flowing through the circuit and protects our appliances from getting burned because of excess current. But how does the fuse work? Well, that we'll study in the next chapter. Also note that we say the power of the bulb is 100 watt when it is connected to 220 volt. If it were connected to, say, 280 volt, then it would consume more electrical power. It would use, let's say, 150 joule per second, which could be dangerous for the bulb. On the other hand, what if you connect it to a low voltage, let's say just 100 volt? Then it won't be efficiently working. It will consume less energy per second and it will not give us a bright light. The bulb will glow less brightly when the voltage is less, which makes sense. Now, the household consumption of electrical energy. Energy is power into time. That is VIT upon 1000 if you want it in the unit called kilowatt hour. And the cost of electricity is electrical energy into cost. So we'll be doing numericals based on this. But here's an example. If an electric oven of power 3 kilowatt is used for 2 hours each day. So that's 3 into 2, 6 kilowatt hour per day. The electrical energy consumed by the electric oven per day will be 6 kilowatt hour. So in a month, assuming 30 days, totally electrical energy used is 180 kilowatt hour. Please understand, kilowatt hour is the unit of electrical energy, not electrical power. So the cost will be this multiplied by 4.50, that is rupees 810. And finally, the heating effect of current. When current flows through a conductor, it starts heating it up. In fact, for an electric iron, we use filaments which heat up a lot and give a lot of heat, like nichrome. Here, we will notice that the amount of heat produced, here we are using H for heat, is directly proportional to the square of current. That means, yes, more the current, more the heat energy produced, yeah, but if you double the current, you'll get 4 times more heat because there's a square here. Next, it depends on the resistance. Higher the resistance, more the heat produced. That is why tungsten produces a lot of heat as well. That's a wastage. And of course, it depends on time. If you pass current for a greater time, more heat is produced. So if you combine them, you get the total heat produced is I square RT, which is something we have seen before as well. If you see here, the total electrical energy formula is I square RT, and electrical energy is nothing but, it can be assumed to be totally converted into heat energy for a heating appliance. So that's how heat is I square RT. But if you want the answer in calories, then please multiply the answer by 0.24. But the SI unit is Joule, however. And this relationship is called Joule's law of heating. And remember, 1 calorie is around 4.2 Joule.
Hi students, this is AJ sir.
If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.